Okay, today is the second lecture for our Vesper theories. And so we're going to cover a little bit more about molecule shapes, and then we're going to move on into some of the other bond theories, such as hybridization and molecular orbitals. So remember that when we talk about geometries of molecules, there's two things to be concerned with. There's electron geometries and molecular geometries. Electron geometries are going to be the ones where it doesn't matter whether your domain or your electron group comes from an atom or a lone pair. It's going to be the base one. So for BRF3, when we look at this, there should be a bromine in the middle, F, F, and F. We should have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we should still have left over. So that's 2, 4, 6, 8, 10, 12, 13, 14, 16, 18, 20, 22. We should have 20. We should have a total of 28 electrons, and this is 24 of them. So we should have 2 more here. So we have 5 electron groups. We have 3 atoms, 2 lone pairs. So that means that our electron geometry is going to be trigonal bipyramidal. So that gives us one of these first 2 shapes here. From there, when we look at it, we want to think about where our lone pairs should be. Now, our lone pairs, when we stick them on in the trigonal bipyramidal, that means that they should be going in at the equator position. So if we imagine that that was our axial position and we have a triangle here in the middle, then we should be putting them here on the equator or the equatorial position. So this should give us our T shape, which is the answer that we're looking for. So remember that molecular geometries are the ones that take into account the lone pairs. Electron geometries are the ones that don't. Looking at this one here, we want to determine the electron geometry of the labeled oxygen. So that's this oxygen there. And so in order for us to do this, we have to put in the rest of that Lewis structure. So when we look at this oxygen, in order for it to have a valence shell, it needs to have 2 or 4 more electrons. So it's got to have 2 more lone pairs to it. Because it has 1 single bond to this carbon, 1 single bond to that hydrogen. So that would only be 4 valence electrons. So we know there must be 2 lone pairs that we can't see. This lets us know that we have a total of 4 electron groups, and that gives us an electron geometry of a tetrahedral. And so that's the type of thing that you're trying to solve with them. Remember that when you want to predict the shapes, your very first part is you have to be able to do your Lewis structure. If you can't draw your Lewis structures, then it doesn't matter. You won't be able to get the correct shapes because you won't know which atoms are connected and you won't know how many lone pairs. So you have to do Lewis structures first. Without your Lewis structures, it can be a very big challenge to create your correct shapes. When there's multiple central atoms, make sure that you talk about each of those atoms for your carbon and your oxygen. So you want to make sure you describe them each individually. So in methanol, this carbon here has a tetrahedral in its shape. And we can see that because it has 4 atoms connected, no lone pairs. For this oxygen, this is similar to that oxygen we had just described. It has 2 atoms connected and 2 lone pairs, which is how we get its bent shape. So that's what we covered last time. And so if you haven't worked on your lab and you haven't gone through that lecture, then you want to make sure you take care of that part. That's the basis. And from there, we're going to build our next parts. So today, what we're going to do is we're going to combine our polar bonding with our molecules. So remember that polar covalent bonding is that a covalent bond means we're sharing those electrons between the 2 atoms. Now, when we have a covalent bond where it's balanced, then those atoms can result in an equal share. But in polar covalent bonding, there's unequal sharing of the electrons. That means one atom pulls the electrons closer than the other side. So that means that one end of the bond has a larger electron density than the other because it has a stronger attraction to those electrons. So this is called bond polarity, and this is the creation of a polar covalent bond. An ionic bond is kind of this to an extreme. Instead of sharing those electrons now, one atom has taken the electron, become the anion, and the other one has given up and become the cation. So polar covalent bonding is kind of partway between there. They're still sharing it. They're still sharing custody of that electron. It's just spending more time with one of the atoms than the other. So the end that is electron deficient gets that partial positive charge. So if you don't spend as much time with the electron, that atom gets the partial positive. The one with the larger density gets the partial negative because it's holding on to those electrons a little bit more. And so this is kind of a visualization of that. This is hydrogen and fluorine, and hydrogen has electronegativity of 2.1, fluorine has 4.0. And so that's definitely going to give us an unequal sharing. Remember that this difference, if it's less than 0.4, then we can consider that to be just purely covalent, they're sharing evenly. But if it's anywhere from 0.4 all the way up to 1.7 or 1.9, we can consider that to be a polar covalent. And so in this case, we see this partial positive over by that hydrogen. And that's what this symbol stands for. That symbol means that it's partially positive. It's not a complete positive charge. It just means it's on its way there. And then our fluorine, because it's attracting those electrons a little bit more, is going to be our partially negative. Now, for our molecules, we now can talk about polarity for molecules as well. Now, in order for a molecule to be polar, it has to have polar bonds. So if all of your bonds are evenly shared, then we don't consider that molecule to be polar because there's no difference in each of those individual bonds. The second part is that those bonds, the polarity of those bonds has to be uneven. Now, the reason why we care about polarity is polarity affects the intermolecular forces. It starts to change how molecules interact with other molecules. This is what we're getting into in our next chapter. And so this starts to impact things like that. Non-bonding pairs affect the molecular polarity because they are going to change that geometry. They have a strong pull in its direction. And then they help create our unsymmetric shapes. And so let's see what one of those looks like. So let's take HCl as an example. HCl is a molecule, and we can see that this bond between H and Cl is polar. This is going to be our partial positive. This is going to be our partial negative. So the bonding electrons are pulled towards the chlorine end of the molecule. And so as an entire unit, we can see that there's this draw towards chlorine side. Now, for something like CO2, this individual bond between O and C is polar. Carbon is not as electronegative as our oxygen. And so it's partially positive to that oxygen's partial negative. And that's what these arrows down here are being drawn to show. Now, when one is being pulled, or when one oxygen pulls those electrons away from the carbon, on the other side of it, we have the other oxygen pulling away from that carbon in the same amount. This means that as a molecule, we still have a partial negative, and a partial positive in the center, but it gives us this net result of there not being one side that's positive and one side that's negative. Because they're pulled equally away from each other, they kind of cancel each other out and they balance themselves. And so while CO2 has polar bonds, it's a non-polar molecule. So when we're looking at the polarity of molecules, we're looking for whether they're balanced or unbalanced. A balanced molecule is going to be nonpolar because all of its electrons are being balanced out. The pole of them are in concert with one another. An unbalanced molecule is polar. And so an example of this is water. Now, water looks in many ways similar to carbon dioxide. We have a pole of that oxygen and that hydrogen, and we have two of them, and they look like they're working against each other. So this hydrogen and this oxygen bond is polar. So is this one here. Now, both of them are kind of pushing inward. And so while this one pushes, you would expect our molecule to go to the right. And when this one pushes, we would expect the molecule to go to the left. But because they're both pushing inside at the same amount, we really don't see a change left or right for this molecule. That part appears to be balanced. But what we do see is that both of them are pushing up. And since there is no molecule, or sorry, no polar bond pushing down, then we are going to end up being a polar molecule for this top side, just like we see here. Those hydrogens give us a partial positive. That oxygen becomes a partial negative. And so overall, our molecule becomes polar. So to help visualize these things, when you work with molecule polarity, you want to draw these arrows here. Now, these arrows are what we call dipole moments. And so it's measure of the bond's polarity. So a dipole gets its name because it has two poles. It's got a positive pole and a negative pole. And this is directly proportional to the size of the partial charges and the distance between them. So the larger your En difference, the larger the dipole. And generally, the more electrons two atoms share, and the larger the atoms are, the larger the dipole moment can be. So our dipole moment is kind of like those, so for bond dipoles, it's between each of those two atoms inside of the bond. For the entire dipole moment, we can also use this to discuss the polarity of the molecule. So we can see those kind of used in two different ways. We can talk about the entire molecule, or we can talk about it for just the bonds. Now, if the entire molecule has a dipole moment, then we can consider it to be polar. If there is no dipole moment, then we can consider it to be nonpolar. So what we're doing with the arrows is we're helping draw out those bond dipole moments to give us an idea about whether or not the polarities are balanced or not. And so we do this by doing something called vector addition. So a vector is an arrow that has a length. So we use them to kind of indicate how strong of a polarity we see, as well as what direction it's going in. So when we talk about that carbon to oxygen has a polarity, then we can use one of these dipole arrows to show that. Now the arrow is always going to start from the positive side, and it's going to point towards the negative one. Now, how we tell the difference between a vector and an arrow is a vector has an end, which means it's got that little line. Let me change this color. This part right here, that little line coming down, that's letting us know that that is a vector. Now, H and F might have a similar direction. Made that one a little bit too long. as our C to O, but the electronegativity is a lot larger. And so we should have a longer vector for them. So the length of the vector indicates the strength of the polarity. So for two vectors to cancel out, they have to be not only pointing in opposite directions, they have to be equal to each other. So when we have our vectors, if this was our, let's say, H, C, and N, we might have all of those vectors moving in the same range. And that means that our entire molecule might have a dipole moment that looks like that one. On the other hand, if we have something where this might be F, or not F, Cl, S, and F, you can see that there's pull from the Cl away from the S, and that's in conflict with the pull towards the F. But those vectors are not equal to each other. This chlorine one is not as strong as this fluorine pull. And so overall, we still see a dipole moment for the molecule moving towards that fluorine because it can overpower the pull towards that chlorine. That's different than our carbon dioxide example, which would be like example number 3, where we're having an equal pull in opposite directions. And since then they perfectly cancel out, then we end up with a non-polar molecule. So not only does the length of them matter, but also their direction. And so anytime when your vectors don't cancel, you're going to be polar. Whenever your vectors do cancel, then you're going to be nonpolar. And so when we start to put out our 3D shapes, then we can start to predict whether we're going to be polar or nonpolar. And you have to remember that the reason why we have to use our 3D shapes instead of like our Lewis structures is our Lewis structures might have us look at something like this. And when we put in our bond polarities, we might look at this and say that this is nonpolar. But that's not true. When we go back and we look at this 3D shape, it really looks like it should be a tetrahedral. And so we get some separation here. As there's this imbalance towards this right-hand side. And so we really are a polar molecule because of its 3D shape. So when you want to predict the bond polarities, or sorry, the polarity of the molecule, we have to draw the Lewis structure and determine its molecular geometry. Once you have its molecular geometry, then you can determine whether the bonds in the molecule are polar. And then from there, we can determine whether there's a net dipole moment. That means whether the entire molecule has a dipole. Now, there is a simulation that I'm going to link into today's lecture that you guys can use to practice this, to kind of build some of those molecules. And so it's one of those PhET simulations. And so you can start with either the 2 atoms or the 3 atoms, right? We'll start with the 2. Right now you can see that this is showing our bond dipole. And we can turn on whether we have the colorings for positive and negative. We can show just where there's more electrons, or we can do none. So I like to use the positives and negatives. It gives me an idea. And from here, I can change the electronegativities. So you can kind of see that when they're both the same electronegativity, we don't see a bond dipole between them. As we start to increase that electronegativity towards B, then we start to see that negative charge flowing from A to that B. The larger the difference, the longer that arrow gets, and the more pronounced the positive and the negative becomes. It doesn't matter whether they're both on the far side of the low electronegativity, or if they're both on the strong side. If they're the same electronegativity, then we're not going to see a difference. And so now look at what direction the arrow changes. Before, when we first started off, our B was more electronegative, and so the arrow pointed towards that B. When we flip that, A is now more electronegative than B, and so our arrow is pointing towards the A. The arrow always points towards the negative side. The start of the arrow is always towards the positive. Now with 2, it's not so bad, but this becomes different with 3. And so what we're going to do is we're going to just keep our bond dipoles on, and we're going to look at that molecule dipole later on. So right now we have 3 atoms here, and you can see that they have this bent arrangement on. So we're going to start them off all being equal. So we have no bond dipoles. And when we click on this, you can see that the molecule doesn't have a dipole as well. Now, what I'm going to do is I'm going to slowly increase this electronegativity of B. Now this is kind of like H2O. And you can see that as we increase the electronegativity of B, we now have these bond dipoles going from C to B or A to B. So as a whole molecule, well, this one is pushing down and to the right, and this one's pushing up and to the right. And since they're both pushing the same amount down and up, then we don't expect there to be much dipole moment going down or up. But both of them push to the right. And so as an entire molecule, we do expect there to be a molecule dipole to the right because no one is pushing back towards the left. And that's what we see here. Now, if I pulled this C so that it was directly across from A, you can see that this one's pushing down and to the right, this one's pushing up and to the left, and now our molecule shouldn't have a dipole anymore. It should be balanced. And so when we click on that molecular dipole, we don't see it anymore. And so that's what you're looking at for these for this simulation, is you can practice with these 3 to try to determine where you think there should be a dipole and where there shouldn't be. If we start to adjust this one, let's make C more electronegative. You can see that now we have a molecule dipole going in that direction as well, because now they're all moving this way. No one is opposing it. If we pull this the other direction, pull it this way, we can switch it to point towards A. So your dipole or your molecule polarity is all about these individual bonds and how they compare with each other. If I bring this to middle, you can see that by me adjusting the position of C, we can change where that molecule dipole is going to be facing towards. If it's bent or if it's linear, it gives it a different polarity. And that's what you're going to be working on with your Lewis structures and then your molecular geometries, is determining whether a molecule is polar or nonpolar. Remember that polar means that it's going to have this molecular dipole moment. Nonpolar means that everything's balanced, kind of like this, and we don't have a molecular dipole anymore. And so I will link that into your lecture for today. Now, this polarity is going to be a big deal when we get into our next chapter. We actually can see that it impacts how our molecules interact with each other. One big example of this is why oil and water don't mix. Oil is what we consider nonpolar. It doesn't have those bond dipoles, whereas water is going to be polar. And so oil likes to stay all together, all of its nonpolars with nonpolars, whereas the polar molecule of water likes to stay with the other water molecules that are polar. And so that's why those two do not mix. And so this all comes from our Lewis theory. Now, Lewis theory is good at predicting these properties, but doesn't give us a good numerical prediction. So it doesn't give us things like bond strength and bond length. But it's a good first approximation of the bond angles that we get in the molecules. So Lewis theory, while it cannot be, while it has its limitations, it's generally a good starting place. It's kind of like resonance. While we can't give just one correct structure, we can use many molecules with resonance to help kind of show where things should be leaning towards. The other one with Lewis theory is it doesn't predict the correct magnetic behavior. So Lewis theory is a starting point, and so now we have to go a step farther than that. And that's going to be us moving into valence bond theory. Now, valence bond theory was developed by Linus Pauling and others, and it basically uses quantum mechanic principles to get an idea about how our molecules are being built and the shapes that they're going to take on. So what they reasoned was that the bonds between atoms would occur when orbitals of those atoms interacted with each other. So in order for us to share those electrons, then those electron orbitals have to be able to interact with one another. And so it depends on whether those orbitals align along the axis or outside the axis. So this is an example of it. If we have two hydrogen atoms, if we put them right on top of each other, there's no energy there, gained there. It means that those electrons are overlapping so much that their repulsions overwhelm the benefit that they get from seeing a second nucleus. So us adding in a second nucleus gives some attraction towards that electron, but also put in so many of those other electrons that it kind of repulses them. But if we start to pull those two hydrogen atoms away from each other, kind of like what we have here, now we've moved so far away that this second nucleus doesn't really give us much of a benefit towards being attracted to those electrons. And so what we found out is that there's a specific range where we're as close as possible so we can really get the benefit of that other nucleus. But we've also minimized the overlap of the electrons. And this is how we start to use the valence bond theory to predict our bond length. The lower the energy, the stronger the bond. So this orbital interaction idea is the basis of the valence bond theory. So as two atoms approach, the half-filled valence atomic orbitals on each atom interacts and they form this new thing called a molecular orbital. Now, molecular orbitals are regions of high probability for finding those shared electrons. So it's just areas where our electrons that are being shared should be. Now, they are going to be more stable than the separate ones because they contain paired electrons shared by both atoms. So those electrons get a benefit because they're shared by two nuclei. And so the potential energy is lowered in these molecular orbitals compared to a total of two paired electrons in separate ones. Right? So us being paired inside of one orbital ends up being a lower energy than having each of them separately in their own orbital. And that's the idea behind the bond. If it wasn't true, then the bond should never form. If the electrons are in a lower energy state by being separated, then there's no reason that they would ever come together. So these molecular orbitals occur because it's better for them to be together than for them to be apart. So this is the orbital diagrams for our H2S. We can see hydrogen's got one opening here in its 1s orbital. And sulfur has two openings in this 3p. And so you can kind of see down here at the bottom that they've made these new molecular orbitals where that 3p that had an opening could align with that 1s, and this 3p could align with the other one. And they could fill in those new gaps inside of that orbitals. So this works great when we're dealing with hydrogen because hydrogen only has that one opening and that one is a sphere, so it can really align well with any of those different parts. But an issue shows up, which is that the number of partially filled or empty atomic orbitals doesn't always predict the number of bonds or the orientation. So carbon, when we make our Lewis structure, carbon forms 4 bonds. But when we look at the orbital diagram for carbon, carbon only has 2 unpaired electrons. So it doesn't predict that it should make 4, it predicts it should make 2, maybe 3 if it uses that empty one. But it doesn't create the same structure as what we see. And so this is where hybridization comes in. So just like in your lab, how you've been filling in how things hybridize, that's what's going on for our molecules here. So hybridization is going to give us new types of atomic orbitals. Right? These are the ones that happen because of the overlap in our bonding. So one hybridization of carbon is to mix all of the 2s and 2p orbitals together, and so we get 4 orbitals out. So what that is saying is that we take all 4 of these orbitals and we make a new one. We make a new set of orientations where they all have the same energy. And we wouldn't call those s orbitals or p orbitals. Instead, they're going to be a mix of those two. So we're going to call them sp orbitals. And in this case, because we're making 4 of them, we would call that sp3. So the valence bond theory, this idea is that valence electrons in the atoms in the molecule reside in the quantum mechanical orbitals. So they reside in s, p, d, or f. Or they reside in the hybrid combination of them. So they exist in those orbitals just like we did in quantum theory, or they exist in this combination between them. And so a chemical bond results when these atomic orbitals interact. And we get 2 electrons in a new molecular orbital. For this to happen, the electrons have to be spin paired. That means one has to spin up, one has to spin down. That's why each orbital only holds 2 electrons still. And so the shape of the molecule is determined by the geometry of these interacting orbitals. If they interact in the hybridized ones, they can take on one geometry. If they interact in the traditional unhybridized orbitals, they can take on another. So hybridization is this idea that they might change their orbitals in order to maximize bonding. So the more bonds that occur, the more full orbitals that occur, and the more stability there is that's present. So hybridization is mixing different types of orbitals to make new ones. So this is a mix of an S and a P. This is a mix of an S and 2 Ps, right? On and on. Now, the same type of atom can have different types of hybridization. It depends on its bonding. So the hybrid orbitals kind of follow this set of rules, that the number of standard atomic orbitals combined gives you the number of hybrid orbitals formed. So that means a 2s combining with a 2p gives 2 sp orbitals. Now, hydrogen and helium are an exception to this because they can't hybridize because their valence shell only has one orbital. So hydrogen never hybridizes because it has no p orbitals for it to move into. But all of the other elements can. That does mean that something like carbon has no d orbital, so it can't make an sp3d hybridization. And so there are some limitations to what you can hybridize. So the number and types of standard atomic orbitals combined determine the shape. And the particular kind of hybridization that occurs is the one that is going to give us the lowest overall energy. So when we look at it, the problem that we ran into was that if we just have S and P, all of our orientations, our S's are spheres, our P's are dumbbells. And so those overlaps would never give us something like a tetrahedral. That hybridization is what allows that to happen. So the formation of an sp3 hybrid, it's taking this one s orbital and it's overlapping it with these 3 different p ones. And so instead of having a circle and then 3 dumbbells, we end up with 4 different orbitals. And you can see that each one kind of points towards the corner of the tetrahedron, giving it its shape. So in some ways, they came up with this hybridization to mirror the molecular geometries that we already started to see, or the electron geometries that we started to see. So they used those 2 things to combine with each other. So sp3 hybridization means that you have 4 electron regions or domains, which is giving us that tetrahedral. And this would be our new orbital diagram for carbon in sp3 hybridization. So valence bond theory is kind of the overlap between atoms with their atomic or hybrid orbitals with each other. So to interact, the orbitals must be aligned between the axis of them, or they have to be parallel to them. So this is an example of the sp2. And so sp2 gives us this trigonal planar shape down here. And if we count how many orbitals we should make, we should have 1 from the s, 2 from the 2p, and so we should make 3 orbitals, which really creates 3 regions. And that's why sp2 and our trigonal planar is tied to that concept that we see with our 3 electron pair geometries. Now, inside of our bonds, you can notice that we don't count our double bonds as being new regions. And that's because they interact in a different way. Our sigma bonds are going to be these overlaps, and pi bonds are going to be something that's a little bit different. So we're going to look at an example of this. This is a carbon connected to 2 hydrogen and double bonded to an oxygen. And so you can see that this carbon down here, it needs to have 3 regions for it to interact with. And so it's going to hybridize sp2 to form those 3 regions. It needs 1 orbital to interact with the hydrogen, another one with the hydrogen, and 1 more with the oxygen. These hydrogens, they don't need to hybridize at all. Because they only need to align with 1 atom. So they just need to use their 1 the one unpaired orbital to line up with carbon's hybridized one, and that would still form this bond. Oxygen, on the other hand, oxygen is going to form a double bond. So that means we have to have two orbitals to overlap. The first one is this one shown here, and it's called the sigma bond. And it's going to be between carbon's sp2 and then one of oxygen's p orbitals. The second part is that when we have our carbon has an open p orbital for it to do its interactions with. And so its orbital kind of sticks up like this and like this. And oxygen had a similar p orbital that was ready to interact. And so what happens is that they form this above and below bond called a pi bond. And that's how they're going to form that second orbital. So they're not going to hybridize. They're going to form that double bond using an unhybridized p orbital. So this is what this is helping us visualize, is that you can see that from carbon's half filled and oxygen's half filled, that there's this connection that they can share above and below that's giving us this new shape here, which is called that pi bond. So for our types of bonds, we have two. The first one is called a sigma bond, and this is when the interaction is along the axis. So that means that they're directly between our two atoms. So if this is our carbon and this is our oxygen, then the bond that occurs here let's say half from the carbon, half from the oxygen, because it's in line with their axis, then this is going to be the sigma. The pi bond results when we have a double bond or a triple bond. And that's because they have atomic orbitals that are parallel to each other and perpendicular to the axis. So using that similar setup of our carbon and our oxygen, the pi bonds happen because they have these, we just draw the top one, orbitals up here pointing parallel to each other but perpendicular to the axis. And so that overlap that forms between them is going to be our pi bond. So the interaction between parallel orbitals is not as strong. And so sigma bonds are always going to be stronger than our pi bonds. So looking at that image again, we have a total of 3 sigma bonds. We have a sigma bond between carbons hybridized and hydrogen. We have another sigma bond between carbons hybridized, and oxygen. So between carbons hybridized orbital and oxygen. And then that second double bond is going to be our pi. And that's going to be the unhybridized carbon with the unhybridized oxygen. So the overlap between a hybridized orbital and one atom will always result in the sigma. More than one bond is when we're going to form these unhybridized p orbital overlaps, which is going to give us our pi. So a single bond, so a single bond is always one sigma bond. It's the stronger bond, so it will form first. A double bond will always be one sigma and one pi bond. And the triple bond is going to be one sigma and 2 pi bonds. Now, the reason why we can only have one sigma bond is that this space is taken up by our sigma. So we can't put another bond there because it's already filled in. This isn't true for pi bonds because while we have a pi bond that's on the top and the bottom, we can also have a pi bond that's coming forward between the carbon and the oxygen and backwards between the carbon and the oxygen. So if you imagined, we could have a pi bond, or for the triple bond, coming along that plane of that green for the second pi. And so that's how we're able to have a triple bond. The reason why there's no quad bond is we can't place another orbital without having it overlap on the other ones. Now, this is very interesting because what this means is that for bond rotations, if the bonds are just sigma, then they can rotate freely because the rotation doesn't break the interaction between the orbitals. But whenever we get a pi bond, so whenever there's a double bond or triple bond, we can no longer rotate around that axis because it would break. So in a single bond like this, we can actually spin either side of this molecule independently around them because they're all sigma bonds. They're all single bonds too. That means that there's no restriction between them. But once we make a double bond, just like we did here, now everything's locked in for their locations. We can't spin around it because we would have to break and unbreak these overlapping pi bonds. This ends up being some interesting chemistry that you're getting into in 121, where we end up having to give different names for similar molecules because where they're connected in the same way, their orientations are different. And so they're in something that we call isomers. And that happens because they can't spin. So we're just going to quickly go through what those other colors or what those other hybridizations kind of look like. SP gives us our linear shape because there's 2 electron groups, hence 2 orbitals. We get that because we have a single bond, or in this case, we have a triple bond with our nitrogen, so we should have 1 sigma and 2 pi. We've already done sp2 and we've done sp3. Now, if we have 4, then we can't be sp4. There's only 3 orbitals for p, and so that's when we have to expand into the d. And so this is when we have 5 electron groups. And you notice why we can only have an expanded octet in period 3 or greater. We have to have that d orbital in order for them to be able to hybridize. So this is how we get that trigonal bipyramidal shape. And it comes because we hybridize the s, the 3p orbitals, and the d. And so that's how we can create all 5. You can imagine that our next one up then must be our sp3d2, where we're taking an additional d orbital and we're hybridizing it as well, which is giving us that octahedral shape, which is the sp3d2. So what we need to know about hybridization is we do need to know that it makes these sigma bonds, and we're getting them by mixing those orbitals together. All of the hybrid orbitals have the same energy for that molecule. So instead of being segregated as 3s being a lower energy than 3p, which is a lower energy than 3d, we mix them all together to form one set of our hybrid orbitals, all with the same energy. And so our hybridization is tied directly to our number of electron groups. So if you look at your number of electron groups, you should be able to tell your hybridization, your number of electron groups is equal to the number of hybrid orbitals you need and so we should be able to tell the hybridization scheme from that. know that S is just one orbital. P can be at most 3 orbital max. And D can be 5 orbitals as a max. Though for us, we're really never going to go past 3D2. So you can see here, if we have 4 electron groups, then we have to have 1 from the S, 3 from the P to give us a total of 4. 6 electron groups, we have 1 from the S, plus 3 from the P, plus 2 from the D, which is giving us 6. So that's how it works. So when you're ready to do your hybridization scheme, you got to draw your Lewis structure first, then use VSEPR theory to predict the electron group geometry, and then from there, you can match it up with your hybridization. For the bonding scheme, which is what we're going to be working on next, is that we're going to be wanting to move on to looking at how they overlap to create this scheme here. So we want to write which ones are sigma bonds, which ones are pi's. Then we should be able to say which ones are overlapping between them. And so that's the next challenge for that part. For this video, we're going to stop there so that way you can go ahead and work through your different Lewis through your lab and fill in your rest of your hybridization and your molecular dipoles. We're going to do a second part of this where we're going to look at what MO theory is. And so MO theory is kind of the next part of our mixing, and it's going to be the next part that we work on.